Okay, and so for the last talk, we have first of our fellows from the databases program. Mikaël Monet is gonna talk about his selected research interests.
J'essaye, mais je fais ça d'habitude. Celui-là. Ah, il le voit ici. Ah, donc, c'est en QWERTY. Là. Sorry about that.
Yeah, you can send the slides.
Okay. Can I use I have my slides on the internet, so yeah. If your laptop works.
Oh, that's the bottom. Oh,
So it was connection with this. Oh, super. This is the number one. So, hi. Yeah. So, hi everyone, I'm Mikaël Monet, and I will talk about a few things about my research. So it's going to be a mix of unrelated things, hence the very uninformative title. First, let me present myself. So I did my PhD at Telecom Paris with Pierre Senelard and Antoine Amarelli on combined complexity of heuristic query evaluation. And after that, I did a postdoc in Santiago in Chile with Pablo Barcelo. And since 2020, I have a research position at INRIA Lille in France. So my main research area, I would say, is uncertain data, also related to provenance and knowledge compilation. I will explain this a bit in the few slides. So as you know, data in the real life can be often uncertain, meaning that you can have, for instance, missing values, or you can get data from inconsistent sources, or you can obtain data through machine learning techniques that are not that can be imperfect. And so somehow we need methods to manage this uncertainty instead of just ignoring it and maybe getting wrong or imprecise answers. And for relational data, we have two main models for modeling uncertain data. We have probabilistic and incomplete database. I'm going to focus mostly on this probabilistic one, this talk, to explain what are the difficulties. So the simplest formalism of probabilistic database is what's called a tuple-independent probabilistic database. And what is that? So this is just a usual relational database, so with relations, tuples, and so on. but it is probabilistic in that every tuple is annotated with a probability value, which is the probability that the data item is true. And so this defines the probability distribution on all the possible subset of that database that we call the possible words. For instance, the probability of the possible word where we have removed the first and the third line is going to be given by this formula, which we say we keep every tuple independently according to its own probability. Now, when we have a query, so this is a simple Boolean query that usually the answer of which is just yes or no on a usual database. And here it's not going to be yes or no, it's going to be a probability. And this value is going to be defined by the sum over all possible words of the database that satisfy the query of the probability of that possible word. Okay. So obviously, in general, we don't want to do this exponential sum because it's too big. And so the question in the area is also for which kind of queries you can compute this in polynomial time or not. So for this specific query, if you think a bit about it, you will quickly see that we can, given as input a database like this, we can compute its answer in polynomial time. So for other queries, it is intractable, so it can be sharply hard. And one of the tools that we have to compute the probability of such a query is what is called provenance. So I don't know if you were there for the seminar by Valtanen last 2 weeks ago. But so provenance is of a query in a database. You can say that it is a Boolean function whose variables are the tuples of the database, and that represent what are the combination of tuples that can make the query true. So if I take again this simple database on the same query, I can express the provenance of this query on the database as a propositional formula, where the variables here, they are the tuples of the database. And here we see, for instance, that we have to have either Alice and Bob that apply to INRIA, or Alice and John, or Bob and John that apply to INRIA. So because this is just a Boolean function, you can represent it in any way that you want. In fact, you can do it in formula or circuits or whatever. And what's interesting about this is that we can use this for probabilistic evaluation, for instance. So by this definition, if you want to compute the probability that a probabilistic database satisfies the query, if you have computed its provenance in a form, so this is a Boolean function, you can then compute the probability that the Boolean function evaluates to true, and this is going to be exactly the probability that the database satisfies the query. Unfortunately, this is generally intractable for arbitrary Boolean functions. And so this is going to depend on how you represent the Boolean function. As you know, there are many ways of representing Boolean functions, so truth tables, propositional formulas in DNF or CNF, binary decision diagrams, and so on. And so knowledge compilation is this field that studies the possible representation that you can use to represent Boolean functions, and what are the properties that they should have if you want to solve, say, sharp-sat or just satisfiability and so on. And they study all kinds of restricted classes of Boolean circuits with horrible names, such as DDNNFs, DDECDNNF, DSDNNFs, and so on. Sorry, you don't. Yeah. So that was one part of my research. You can also use provenance not only to do probabilistic evaluation, but you can also use it to compute what's called Shapley values. So if you have a fact F that is in the database, you say that the Shapley value of this fact for the query Q on the database D is going to be a value, and usually it's going to represent the importance that this fact has for the query. So it's the higher this value will be, the more relevant the tuple will be to answer your query. And so what we showed recently with co-authors is that if you can compute a particular kind of circuit that's called deterministic and decomposable that represent the provenance of the query in the database, then you can compute this Shapley value also in polynomial time. Similar result for another score from machine learning. Something else that I wanted to talk a bit about is hardness result and counting weighted matching for unbounded-treewidth graph families. So this has nothing to do about databases at all, but there will still be a bit of probabilities. So I'm interested in the following problem. You fix a graph family J of undirected graph. And then for this graph family, you define the following problem. As input, you get a graph of the graph family and probability values on the edges. And what you want to compute is the probability that you obtain a matching of the graph when you just select or not each edge independently. So if the graph family has bounded treewidth, then you can do this in polynomial time. This is a Volcker result following from Courcell's theorem that you can adapt to with probabilistic in a probabilistic setting. And what we showed with Antoine Amarly, who's here in the room, is we have a lower bound that holds for any graph family that does not have bounded treewidth, and that satisfies a certain treewidth constructibility requirement. We show that for any such graph family, then this problem is intractable. So this is a reduction from I don't remember. Antoine, you remember the problem? It was independent set in 3 regular bipartite or something like this. How much time do I have?
Like 3 minutes.
3 minutes. Okay, so I'll skip this one. And last, I wanted to talk quickly about a cute open problem that I have, which is about perfect matchings in the Boolean lattice. So I guess you all know what is a matching in a graph, but it cannot hurt to recall. So a matching of a graph is just a set of edges that do not intersect and that touch all the vertices of the graph. And so let's consider the Boolean lattice over k elements, for instance, this one. So here, this is a graph, and we draw an edge when this node is included in this node, and the size difference is only 1. So it's really a Haas graph of the Boolean lattice. Then, so this is the same thing. I take a set O, so this will be the orange nodes, of nodes that is upward closed in this Boolean lattice. And I want that it has the property that it has as many nodes of even size as nodes of size that is odd. For instance, here we have 1, 2, 3, 4, 5, 6 nodes of odd size, and then we have 1, 2, 3, 4, 5, 6 nodes of even size. Okay. And I'm wondering if the following is true, then for any k and a set of nodes like this that satisfy this property, then either the orange, the graph induced by the orange nodes, or that induced by the complement has a perfect matching. Yeah. So to have a perfect matching, it has to satisfy this condition because this is a bipartite graph, and so you want that there are as many nodes in the two partitions, of course. And so I'm wondering if this is true. For this specific example, the two graphs have a perfect matching. So the orange graph, you see the perfect matching here in red, and the complement one, you see a perfect matching in green, okay? But there are graphs in which one of the sides has no perfect matching, but the other still has one. So when this one, the orange one, it does not have a perfect matching. So if you look closely at it, you can you will be easily able to see why it doesn't have one. But the complementary one has a perfect matching. And so I tried to prove this maybe a few years ago. I didn't manage. I ran computer search to find a counterexample, but there's no counterexample so far. So if you are, feel free to think about it. That's all. Thank you.
Thanks a lot, Mikaël. Maybe we have time for one question.
Could you just go back to the previous slide to read the problem again? Thanks.
Oh, okay, yeah.
Is there a translation of this into some property of monotone Boolean functions or something? Because presumably there's a Hall condition you want to satisfy.
Yeah, so I tried like applying Hall theorem or Koenig's theorem and this kind of thing. I couldn't didn't find anything interesting to say. But here, the set O is arbitrary. It just has to satisfy this property. The one thing I know is that if you take the set O that satisfies this property but is not upward closed, then this is false. I have an example where this is false. And other than that, I don't know much more. Yeah. So I tried, I think, all possible Boolean lattices with 5 or 6 elements, something like that. And yeah.
Great. Well, thanks, and let's thank all the speakers again. We can meet in 20 minutes. We have one more break.